Hello, my YouTube friends. Today we're going to look at transient analysis of electrical circuits. And basically what transients are, transients is any small disturbance that occurs in the electrical system. And that system can be due to switching purposes or causes of switching. And some other causes may be lightning and so on. But besides that, these analysis has to be done to study, for instance, grid integration of distributed generation systems into the main grid, and then also these studies are also conducted to clear certain faults that may occur in the system. So let's dive in and see what these systems are. So first of all, we look at the definition, which is clearly explaining that any time-varying currents of voltages resulting from certain application of sources, usually switching, are called transients. And then in this analysis, we're going to apply Kirchhoff's voltage law, Kirchhoff's current law, node voltage analysis, and mesh current analysis methods to solve transient circuits. That's why if you look at the previous videos that I've done, in case you've forgotten your how to solve node voltage method or mesh current method, I've done extensive analysis on those methods. You can go back and watch the previous videos to get you back in form. Otherwise, we're looking at current voltage relationships for inductances and capacitances, and these will involve integrals and derivatives, what we call integral differential equations. And these integral differential equations must be converted to full differential equations for us to be able to analyze transient circuits. So in most cases, what you have is, like we mentioned, if we have a DC circuit, we'll have a transient due to switching. That is, if you do the switching on, then the values of voltages and current have to stabilize into a steady state. Or if you switch off a system that was already operating and then you cut off the circuit, then also the new values of voltage and current has to be obtained, what we call a steady state situation. So again, a short-time electrical disturbance in voltage or current is called a transient and may lead to elements having problems. And that's why we have to study and analyze these systems. Now, when we come to the behavior of each element, so we have got the resistor, inductor, capacitor, we have to look at them separately. So when we look at a resistor is one element that reacts instantaneously to the rate of change of current and voltage, implying that before the switch is closed, we have zero current flowing in the circuit. We know that current cannot flow in an open circuit. Therefore, once we close this switch, current will flow, and instantly the resistor is going to have a voltage drop across here, when initially that drop was zero. So we are saying before the switch is closed, this is T0 equal to 0 minus. Before the switch is closed, the current is 0. And then at the moment when we just close the switch, we have a current in the circuit, which is IR equal to V over R. And as you have noticed, the resistor is going to have a drop instantly, a drop of voltage. So it's going to react instantaneously to the change of current, in this case, or voltage. Now, when we look at the inductor behaves slightly different. Before the time t is closed, the current flows through there's no current flowing through the inductor, and at the time when we just close the circuit, the switch is just closed, current flows through the inductor, and the voltage across the inductor may be calculated from VL equal to L di dt. But what happens is that as time tends to 0, the rate of change of current tends to infinity, which corresponds to the voltage across the inductor tending to infinity, which is not possible. This implies that the inductor will oppose instantaneous change of current. So what happens is that if the current in the inductor is 0 at time is equal to 0 minus, then even after the switch has been closed, the inductor at that moment is going to maintain that value of current. If the current was 10, it's going to maintain it at 10. So we are saying at time t is equal to 0 plus, which is the time just after the circuit has been closed, the switch has been closed, the inductor acts as an open circuit. It will not allow any current to flow through it. But as the time tends to infinity, an inductor will act as a short circuit. So the more the switch is closed, the longer the switch is closed, the inductor will act as a short circuit. The capacitor, on the other hand, acts in a similar way as an inductor, but in that its reaction is more focused on the voltage. So whereas for the inductor we're looking at the current behavior, for the capacitor we're looking at the voltage behavior. The capacitor, on the other hand, rejects or opposes instantaneous change of voltage. So how does that happen? When the switch, at the time when the switch is just closed, the voltage across the capacitor becomes equal to the voltage across the source. And the charge across the capacitor can be obtained via this equation. So we have got Q, or what we call charge, is equal to capacitance multiplied with the voltage. So the rate of change of charge then is equal to the capacitance multiplied by the rate of change of voltage. Further on, if we look at circuit, then you notice that as the current across the capacitor or through the capacitor is equal to the capacitance multiplied by the rate of change of voltage, as the rate of change of time tends to 0, the rate of change of voltage tends to infinity, corresponding to the current through the capacitor tending to infinity, which is not possible. And this implies that a capacitor opposes instantaneous change of voltage. So the same voltage at time is equal to 0 minus will appear at time is equal to 0 plus just after the switch is closed. This means that if the voltage is 0 at t is equal to 0 minus, then it's going to be 0 at t is equal to 0 plus. So that's the behavior of the elements. As mentioned, KVL and KCL are going to be applied to determine the solutions for these transient equations or differential equations. But what you'll notice is that the transient or the differential equations that we are going to have are going to be in the format of the first order circuits or first order differential equations. And it's for this reason that we call these circuits first order circuits. So when we look at the solutions that you're going to obtain, or the generalized solutions that you're going to obtain, you're going to have what we call a particular integral and then a combination with a complementary function. But because the first excitation here in this case is equal to 0, what you are going to obtain in this case for the first order circuits that have a source-free response, you're going to only have the particular the complementary function as a solution. But when you have the first response or the first excitation, then you're going to have a combination of the particular integral and the complementary function. So let's look at this is the first order RC and RL circuit. So I'll begin looking at first the RC circuit. In this case, we're looking at a circuit where the switch has been on 1 for a long time. This implies that the circuit has been running current has been flowing into the circuit, and the capacitor initially is going to act as a short circuit until it is fully charged. When it's fully charged, then it's going to act as an open circuit and open up, and then the voltage of the source is going to be equal to the voltage across that capacitor at that time. So at the time when we switch from 1 to 2, this implies that the source is eliminated from the circuit. What you remain with is this circuit, which in this case the capacitor is going to act as a voltage source, and the resistor is going to act as a drainer, or is going to consume what the capacitor has stored. And so we call this a discharge circuit. So the capacitor is fully charged, is going to discharge through this resistor by acting as a voltage source. So we apply KVL. We know that KVL states that the sum of voltage drops across the elements must be equal to 0. So in this case, we don't have a voltage source. What we have is the voltage drop is across the resistor is VR, and the voltage drop across the capacitor is VC. This must be able to give us 0 because the source is 0. And using this, we replace in the value of the voltage drop across the resistor, which is supposed to be equal to IC multiplied by the value of resistance. Therefore, when we look at this equation further, you notice that that's what we have. So we apply KVL, which is what is written here, and we have IR plus VC equal to 0. And when we replace the value of the current I here, which is the current through the capacitor, which is C dVc over time, rate of change of time, plus that, we obtain the equation. When we divide both sides, by RC and here by RC, we obtain the equation 69 here, which is the rate of change of voltage across the capacitor over rate of change of time plus 1 over RC, VC 1 over RC equal to 0. So if you notice, this is the first order format of differential equation, and the general solution to this, because we've got the forced excitation equal to 0, what we are going to obtain is simply a complementary function, and the complementary function is going to give us any letter can be used here, a e to the power minus pt, and so the value of the voltage across the capacitor as a function of time is going to be equal to a e to the power minus t over RC. But this has to be found out. What is A? To find A, we get to use the initial conditions that we know. So in this case, if we know the value of the capacitor value at V at 0 plus, then we can get to find A. So at the time when time is equal to 0, then with VC at 0 plus is going to be equal to A, because this is simply 1, and therefore V is equal to A, and we replace that A by V, and we obtain the value of the capacitor voltage as a function of time to be equal to this here. And you see the capacitor will then discharge from its full charge to 0 with time at what we call a time constant, RC tau. And this is what we call a natural response of the RC circuit. When we come to the inductor, what happens is that in a similar scenario, so we're looking at a source-free response of an RL circuit. When you look at this circuit, you've got the connection at 1, which has been before the switch is turned or is moved to 2. So what will happen is that the inductor is going to get fully charged, and the energy stored in the inductor can be found by half Li squared, which is the value of inductance. For a capacitor, you remember we had half CV squared. This is the energy stored in a capacitor, but for an inductor, it's Li squared. So, and we know that the inductor opposes instantaneous change of current, implying that the value of current that will be when the circuit is connected at 1 is the same value of current that will be maintained just after the switch is closed at time t is equal to 0 plus. So this is what we are saying, as when time is equal to 0 minus, the current is equal to I, and at the time when the switch is just closed, the current is still maintained to be equal to I, because the inductor opposes instantaneous change of current. And what will happen now is that this inductor will act as a current source, and it's also going to drain the current through the resistor. The resistor in this case is going to consume what the inductor energy has stored, and this is what we see. So to find out how do we find the values, we calculate by applying KVL in similar way as we did with the capacitor, only that here we have the voltage across the resistor and the voltage across the inductor, which we solve, which is replaced by L di dt and IR. And so we can divide both sides by L, and what we obtain is di dt, or rate of change of current over time, plus R over L, I, gives us 0. So we are saying the forced excitation in this case is equal to 0. From this, we're able to determine that we're looking at a source-free response, and our solution is simply going to be the complementary function, which in this case is going to be equal to A exponential R over L multiplied by T. And therefore, the current after the switch has just been closed is going to be equal to A. And we can now find, since we know that at time t is equal to 0 plus, the current was equal to I. So if the current is equal to I, A therefore is going to be equal to I. And the solution then gives us, the final solution is the current at the rate of change of time, or as a function of time, is equal to I E minus R over L T, and the time constant then being equal to L over R, which is given in seconds. And basically that is how the inductor is going to act. And in a similar fashion to the capacitor behavior, we are going to see the discharge of current from the maximum value of I to 0 as time tends to infinity. And we can also determine the voltage across that inductor by applying VL equal to L, rate of change of current over time, and we have calculated the value of the current as a function of time, which we replace into our equation 83 and obtain the rate of change of that current. And when we do the differentiation, we come up with the final solution to be equal to VL equal to minus I RE minus R over L T. And that's the response that we get when we get the source-free response of the RL circuit. Next, we're going to look at the forced response of the capacitor as well as the inductor forced response, and then we'll look at some examples.